This conference will now be recorded.
Hello everyone. Last day we have already started isolation of metal from its concentrated ore. So this is basically the second step. Okay, the heading that we are seeing here. This is the second step of metallurgy, and under this second step, some methods we have seen. Now today we are starting from reduction by source of carbon. Actually, there is reduction possible by different methods. This is the first method, which is by using carbon as reducing agent. And after completion of this isolation of metal from its salt, that is this particular topic, the third step of metallurgy, which is purification of the metal, and different processes under this purification will be discussed, and some related problems. So when it is reduction by source of carbon, now it may be carbon itself or it may be carbon monoxide, that is also another reducing agent possible. This process is called smelting. Okay, the reducing agent is commonly a source of carbon, and any of these all are basically source of carbon. Any of these can be used: coke, charcoal, coal. The oxides of less electropositive metals. So see here what type of metals we have. We have lead, zinc, iron, tin, copper. So all these are basically D block elements and also P block elements. Okay, but here we do not have any strongly electropositive metals like S block elements, because they are method for reduction that is completely different. When we are talking about reduction by source of carbon, basically the metals that are used under this process are less electropositive, so they are not from S block. By strongly heating them in blast furnace. So blast furnace, it is such an arrangement where very high temperature we can achieve, and it is done with reducing agent. So see here we have some examples: copper oxide, PbO, iron oxide, zinc oxide. So all these are oxides of these metals, and here we are using reducing agent, either carbon or carbon monoxide. Fine. So CuO, which is having oxidation state of copper +2. Now after reduction, it is becoming 0, and CO is oxidized to CO2. Similarly, PbO oxidation state is +2. Now it is converted to oxidation state 0, and carbon is oxidized to carbon monoxide. So these are the types of reaction that is happening here. And zinc oxide, it can be reduced both by carbon or carbon monoxide. Now gangue, which is basically the impurity, that is the undesired part, it is when mixed with the substance, and this substance is basically flux. So gangue plus flux together it makes slag. So if we are not using this flux, removal of this undesired part, that is gangue, it is difficult. So that is the reason we add flux, so that flux is combined with gangue and it can form slag. Now it will be easy to remove. So flux is basically the substance which is used for removing this gangue. Now when we are talking about concentrated ore, see what is the name of the topic: isolation of metal from its concentrated ore. So concentration of the ore, that is basically the first step, where what we do, we basically, that is ore is concentrated, that is now the amount of ore per unit volume that will be increased. This is the first step, and after this first step, the second step, which is isolation of the metal from its concentrated ore, it is basically all about reduction. So from metal which is present in its ore in different oxidation state, +2, +1, +3, now it will be converted to 0 state, that is metallic, its metallic form. So concentrated ore, which is basically ore plus gangue, that is desired part, this is the undesired part. Then we are adding to it reducing agent, which is mainly carbon, and we are also adding flux. So flux is the purpose of using it. It will combine with gangue and it will make slag. And reducing agent, that will reduce the metals which are in different oxidation state to metal 0. Coke is not used for reduction of H block oxide. Remember what we have said in the second point, oxides of less electropositive metals are only used in this process, but not H block elements oxide, because H block metals are very highly electropositive. So coke is not used for reduction of H block oxide, because whenever you are trying to use coke, so here we have taken calcium oxide, which is H block oxide. Calcium is from group 2, that is H block metal. Calcium oxide, if you are trying to reduce it with carbon, see, you are not getting desired result. What is our desired result? Our desired result is calcium from +2 state. We should obtain it as calcium 0, but you are not getting calcium 0. Okay, so that is the reason here we do not use this process for H block metals. So here, while we add flux, that is the what is the reason behind that? That is mentioned. Flux is added which combines with gangue to form slag, and slag will be separated more easily from the ore compared to the situation when you have not added flux. Then it is difficult to remove these impurities. But if you are adding flux, now flux is combining with gangue. Ultimately, it is forming slag, and its removal will be easier. Now, when the gangue is acidic in nature, we know when it is non-metallic oxide. For example, SiO2, it is non-metallic. That means it is acidic in nature. So when the nature of gangue is acidic, the flux that we will use, obviously it will be basic, because then interaction between them is possible. So here calcium oxide we are adding as flux so that it can react with this acidic gangue and it can form calcium silicate, which is the slag. And if suppose the gangue is basic in nature, that is here iron oxide, that is the undesired part, you want to remove it from the ore. In that case, what we have to use, as it is basic oxide, now we are using the flux which should be acidic in nature, because then only reaction is possible. Because if it is basic and you are adding the flux that is also basic, both are basic in nature, there will be no reaction. So we have to add the opposite nature, that is flux of which is having opposite nature. Okay, so acidic gangue you have to use basic flux, and if it is basic gangue you have to use acidic flux. Here it is producing FeSiO3. Next, so the previous method what we have seen, reduction by source of carbon. Now the second method, here the process is called metal displacement method. So in this case, what we are using some reducing agent, which is another metal, but this another metal which we are using as reducing agent, this must be more electropositive. That means it will have higher tendency to donate electrons. That means it can act as reducing agent. In this case, water soluble compound is obtained from the ore. Okay, so the reaction is happening in aqueous solution of the compound, and the metal that we are using, that must be more electropositive than the metal which you are extracting. Otherwise, this reaction will not be possible. Now, if we see the examples, we have this ore which is argentite, silver sulfide. Now, first, in presence of oxygen, it is converted to silver sulfate. Next, what we are doing, we are using more electropositive metal, which is copper. Okay, so copper is more electropositive than Ag, so that is why you can use copper. Okay, but if you are using any metal which is less electropositive than silver, silver is actually the metal that you are extracting. But if you are adding, that is the metal that we have added, if it is less electropositive, reaction will not be possible. What is the reason behind that? Because copper here it is in 0 oxidation state, silver it is in +1 oxidation state. So copper must give electron towards Ag so that we can get the metallic silver. So copper must be oxidized because it has donated electrons. Now it is +2 oxidation state, from 0 to +2. It is oxidized and silver is reduced. So more electropositive metal means it will have higher tendency to reduce the metal which we are trying to extract. Then another method, same ore we have taken, powdered argentite. First we are using sodium cyanide. See, it is aqueous solution and sodium cyanide is soluble in aqueous solution. In presence of air, first this type of complex is produced. That means from AgS, first we are making this type of complex, and this is the byproduct. Now this complex is treated with zinc. Now zinc is more electropositive than silver. Just you have seen copper is more electropositive than silver. So that is the reason now zinc can reduce Ag, which is in +1 oxidation state. So how we will be understanding that it is having +1 oxidation state? It is very easy to understand, because outside we have one sodium atom. That means here negative charge outside the coordination sphere is -1. So silver is +1 and 2 cyanoligand, that means +1 and -2. So -1 charge is extra, that is neutralized by sodium atom. So here silver is having +1 oxidation state, but after reduction with zinc, which is more electropositive than silver, now we are getting metallic silver in the form of black precipitate. And the place of silver, see, now it is taken by zinc. So that is why this method is known as displacement method, because copper is displacing silver in the first case. In the second case, zinc is displacing silver. So that is why it is metal displacement method. So is there any doubt? The next method will be self-reduction. So when we are saying self-reduction, that means we are not using any external reducing agent. Fine. The metal itself, that is the metal which we are trying to isolate, which we are trying to get in the metallic form, it will itself act as reducing agent. Under this method, what type of metals we generally extract? It is copper, lead, mercury, without using any additional reducing agent. How it is possible? So what is done actually? Sulfide ore is taken, that is sulfide ore of copper, Pb or Ag. It is partially roasted. Now roasting method in last class we have seen, it is basically conversion of the sulfide to oxide. But all the sulfide molecules will not be converted to oxide. Partial roasting, that means some amount of sulfide will be converted to oxide and rest of the sulfide, it will remain as sulfide only. Now it is then reduced to metal by remaining sulfide ore at elevated temperature in absence of air. So with examples it will be clear how it is happening. Here we have taken PBS, that is lead sulfide, in presence of air, because when we are doing roasting, the first method is that you have to do partial roasting. Now you require oxygen. So that is why it is in presence of air. And this oxygen, it is now converted to oxide. From sulfide, now we are oxide. So this is the first method. And in the second method, what we are doing, now some amount of PBS, that is unroasted ore, it is still present, because the first process, it is basically partial. We have not done complete roasting, it is partial roasting. So some amount of PBS will be there and some amount of PBO that will also be there. And when it is heated at high temperature without presence of oxygen, now what is happening? PB, it is in +2 state in both salt, but ultimately it will be converted to PB0. So it is reduced, and sulfur and oxygen together will make sulfur dioxide. So see, as we are not using any external reducing agent, so that is why this method is known as self-reduction. Another example, which is with copper. So the first step is not mentioned. First step is just like here you are seeing that some amount of Cu2s, it will be first converted to Cu2O, which is roasting in presence of air. And in the second method, now there is both oxide and sulfide present. Copper from +1 state, now it will be converted to copper 0. Sulfur and oxygen, it will combine to each other and it will form sulfur dioxide. Okay, so this method is self-reduction method. Is there any doubt? Should I repeat? Number fourth method. Number fourth method, it is electrolytic reduction. Remember in the first method where we have used carbon as a source of reducing agent, there we have mentioned that this process is only for less electropositive metals, not for highly electropositive metals. Highly electropositive metal means from S block. Now you will be seeing that electrolytic reduction, this is basically used for very highly electropositive metals. For example, this S block metals, and also we have aluminium which is from P block, but it is also electropositive. Oxides are strong electropositive metals. They are used in this process, and these are very stable. Now why it is very stable? Because as they are very reactive in nature, they will always remain in oxidized form. So that is why their oxides are so stable. So it is difficult to reduce because their oxides are stable. It will always try to stay in +2 state or +1 state or +3 state. It will never be converted easily to the corresponding 0 state, that is neutral, because it is very reactive. So it is difficult to reduce. Large negative value of E0. That means if you take the system, suppose E0 of M2 plus M or E0 of M3 plus M, depending on different types of metals, then this value is highly negative. It means what? That the reducing capacity of these metals are very high. So it will, when it is large negative value, it will always try to remain in the oxidized form, which is M2 plus or M plus or M3 plus. Okay. So it is difficult to reduce them into the metallic state, that means zero oxidation state, by carbon reduction. So that is why in carbon reduction method, we have not used this type of oxide, metal oxide. So what to do? Such metals are extracted by passing electricity through their fused chloride salt, hydroxide salt or oxide salt. Okay, so it may be calcium chloride, calcium hydroxide, calcium oxide, or sodium chloride, sodium hydroxide, sodium oxide. Okay, here when we are saying that we are using electricity through their fused chloride, so just take for simplicity, take the example of NaCl. So NaCl, it is in +1 state. Now we are using electrical energy to forcefully convert this Na plus to Na0, because this method otherwise it is not very easy to convert from +1 state to 0, because it is always trying to remain in +1 state, not 0 state. So that is why it is difficult. That is why we are using electrical energy to that is electrical energy here will be converted to chemical energy, and this non-spontaneous reaction now we can perform them. Here we have the corresponding picture. We are taking fused salt. That means here aqueous solution is not taken. It is not water. So in the electrolyte there will be only the metal ions and the corresponding anions. Okay. So both cation and anion both will be present. In the left hand side anode is present, and in the right hand side we have cathode. Here during this process, when it is going on, what happens? The molten salt that we have taken, that is a fused chloride, it is not aqueous solution. Metals will be liberated at cathode. We know at cathode reduction takes place. So metal ion, suppose if it is M plus, it will accept electron and it will be reduced to metal 0. Okay, so it is passive metal because the metal that you are trying to convert to metallic state, that will be deposited here. Fine. And the reactive metal, that is it is in already 0 state. So when it is in 0 state, suppose if it is M, now it will be converted to M plus an electron. These electrons will be taken by this M plus, which is present in electrolyte, and it will be reduced to M0. So here oxidation is taking place. M to M plus, and it is liberating electron. So gradually the metal will be corroded. See, it is clear from the picture. It corrodes here, and in the right hand side there will be deposition of metal. Now, depending on the reactivity of the metal produced in the electrolysis, suitable metal should be used as electrodes. That is, we are talking about these electrodes. Okay, it may vary depending on what type of salt we have taken. In this case, sometimes flux we can add to increase the conductivity of the molten mass. Normally, we add flux to remove gangue, because flux plus gangue it produces slag. But here we are using flux to increase the conductivity of the molten mass. Okay, it is molten state, it is not aqueous state. So its conductivity, it will not be very good. But if we are adding flux, it will help to increase the conductivity. And here we are basically, that is based on this equation, this is the principle behind it, that del G naught is equal to minus NF E naught. So N is the number of electrons involved, F is Faraday, and E naught is the reduction potential value. So if del G value, if it is very negative, then only the process will be highly spontaneous. Okay. So by electrolytic reduction method, we do isolation of metal, and it is applicable only for electropositive metals, mostly from S block. Okay. Any doubt? Should I repeat? So 4 methods we have discussed. Now we will see the difference between some processes. Under isolation of metal, we have seen both these processes, not in today's class, but in previous class. Calcination and roasting. These two processes, there is some similarities, some dissimilarities, but as mostly they are very similar. Both are used for isolation, under isolation of the metal. Okay, so that is why there is some subtle difference. So there it is very easy for us to get confused between these two processes. Okay, so that is why we should know properly what is the difference between these two processes. When it is calcination process, ore is heated to high temperature in absence of air or limited supply of air. That means amount of oxygen. Air means what? Amount of oxygen. Amount of oxygen will be very low. But if it is roasting, now see, ore is heated with a condition that it should be below melting point. It is not very high temperature. Temperature must be below melting point of the metal. And now it is in excess of air. Okay, that means high amount of oxygen gas must be present. This is used for sulfide ores. So here, suppose if we have Cu2S, it will be converted to Cu2O. Okay, so sulfide is converted to oxygen. So as it is converted to oxygen, so obviously high amount of oxygen is required. So that is why excess of air. But when it is calcination, it is basically used for carbonated ores. Carbonated ores, or sometimes it may be that you are using some hydrated ore. Hydrated ore means Al2O3 and some water molecules are attached. So when you are heating it, high temperature, these water molecules will be removed. Now it will be anhydrous Al2O3. This is one, that is oxide also you can use, or that is hydrated oxide. And you can also use it for carbonated ores. So when it is carbonated ores, suppose we have any metal carbonate, and when you are doing the calcination process, now it will be converted to the corresponding oxide and CO2 will also be produced. That means calcination process is basically removal of water, either removal of water or removal of carbon dioxide. Here carbon dioxide is produced along with metal oxide. It is clear from this equation. And here SO2 is produced along with metal oxide. So oxygen is basically also react with sulfur and SO2 is produced. So in roasting, the gas that is generated is sulfur dioxide. But in case of calcination, the gas that is generated, it is carbon dioxide. Moisture, organic impurities are removed. See, as I have said, that water may be removed and you are getting anhydrous metal oxide. or organic impurities. That means organic impurities means carbon dioxide atom. Okay. Here volatile impurities are removed as oxide. That means it is talking about SO2, which is volatile impurity. So these are some of the main points of difference between these two processes. Another difference we will also see, which is between smelting and roasting. So what is roasting we already know, but there is another process, smelting. We have started today's class with smelting, right? So where we have seen there, we are doing some reduction using carbon as a source. So metal oxides are heated with suitable reducing agent. Mostly it is carbon or any carbon source, for example, carbon monoxide. But roasting involves heating of ore either alone or in presence of oxidizing agent, mostly O2. So these two are obviously different processes. This is oxidation, this is reduction. Smelting is done in open air at high temperature, and hence it is also known as pyrometallurgy, because the word pyro, it is related to heat or temperature. Roasting is done in reverberatory furnace. That means both processes are done in different systems. In smelting, metals like Fe, Zn, Pb are extracted, and in roasting process, ores of sulfides are actually taken. See this example that we have discussed here. In smelting, impurities are known as slag. Remember, we use gangue, G for gangue, F for flux, and it produces slag, S for slag. In roasting, impurities are of sulfide. So in roasting, basically the impurities are removed in the form of SO2. So in both cases, you are removing some impurities, but impurity nature is different. When it is smelting, the impurity we are calling it as slag. When it is roasting, the impurity is SO2. Fine. Any doubt? Now we have reached the third step of metallurgy. After isolation, that is isolation method, it is all about conversion of the metal from oxidized state to metallic state, that is metal zero. So now we have at our hand the zero oxidation state metal, but that is not the end of metallurgy. Next, what we have to do, we have to refine it or purify it, because still there is some presence of impurities. Okay, so suppose you have already obtained, you are doing extraction of copper, you have already obtained copper in zero state, but suppose if it is 80% pure, so our aim is to make it 99.9% pure, and that is possible if we are doing this purification step. But don't think that this is a single step. There are several methods for purification step, and depending on what is the nature of the metal, depending on that, we will use different methods. So one method, it is not that it is applicable for all the metals. Some methods are specific for some specific metals. The process of metal refining, it is carried out after extraction of metal. That means all the processes that we have discussed until now, that is isolation of metal. After that only you can do purification. It is not that directly you have taken the ore and you are doing purification. No, purification is possible only after extraction of metal. That is another way of saying after isolation of metal. So now the metal from +2 or +3 or +1, from all these oxidation state, now the metal you have already converted it to zero. But next, this metal which is already in zero oxidation state, you are further making it more pure. The impurities like unwanted metals. So as we have taken this example, suppose you have already 80% copper, but still there is some 20% impurity, and this impurity, it may contain any other metal, it may contain some non-metal, unreduced oxide of a metal, it may contain flux, slag, etc. So all these impurities, different kinds of impurities, all can be eliminated, and ultimately we can get pure metal, that is almost 99%. Now these methods, because there are several methods, it is not a single process. different methods, and it is based on the properties of the metal and also the nature of the impurities. So it is not just the nature of metal, you have to consider nature of both the metal and as well as the nature of impurities that you are trying to remove. Here we have the list of all these methods. There may be some other methods also, but these 8 methods are enough. Distillation, liquefaction, electrolysis, zone refining, cupellation, polling, vapor phase refining, chromatographic methods. Total 8 methods are there. All will be discussed one by one. The first method, distillation. Which metals are used in this process? Only those metals you can use which is having low boiling point. And this condition is fulfilled by mercury and zinc. So mercury and zinc can be purified by distillation. Because when we are talking about distillation, basically you are boiling the liquid which is impure liquid. Okay, so when you are saying that it is liquid, that means what? Boiling point must be low, otherwise we cannot convert the solid form to liquid form very easily. We are doing the process with liquid form. That means boiling point must be low. Then only you can do distillation. Fine. The impure metal, suppose if it is zinc, you have taken this liquid zinc which is impure, you are boiling it. Now there will be vapors of zinc. Now this vapor, as here it is closed condition, it will move through this. Okay, and here we are, see there is a tube which is in separated from this outer wall. This is inner wall, this is outer wall. So cold water is supplied. So cold water is supplied means here temperature in this zone, it is obviously lesser than the inside this where it is boiling. Okay, so the zinc vapor that we are getting, it will be now in contact with cold water. So it will, this from vapor form, now it will be in solid form. Sorry, from vapor form it will be converted to liquid form. So now this liquid, it will be stored here. Okay, so in this case we are getting distilled pure metal liquid. The impure metal is heated above its boiling point so that it can form vapor. Now the vapor will be condensed in this condenser. It is known as condenser because it is helping in condensation process, leaving behind the impurities. So impurities will be remaining here, because compared to impurities, the metal that you are actually purifying, that is having low boiling point. So that is why when you are heating it, only zinc will be evaporated and it will be condensed. Ultimately pure zinc you will get it here. But impurities having higher boiling point, they will not be converted to vapor. They will be remaining in the flux. Okay, so this is the method of distillation. Is it clear? Should I repeat it once more? Next method is liquefaction. In liquefaction, metals with low melting points are purified. So you can use this method only for metals where melting points are low. The melting point of the impurities must be higher than the metal. Okay, so you have metal, you have also impurity. I for impurity, this is having low melting point, this is having high melting point. Okay, you have taken this impure metal in this container. First, the metals are converted into liquid state by supplying heat. So here heat is supplied. So as a result, what will happen? Now only the metal will be in liquid form, and as there is a, it is sloping in nature, right? So ultimately this liquid metal, that is a pure liquid metal, it will be stored here, and the impurities that will be left behind, because impurities, as it is having higher melting point, it will not be converted to liquid. Okay, only the metal will be converted to liquid. So metals are converted liquid state by supplying heat at a temperature slightly above their melting point. because it must be close to melting point or slightly greater than, otherwise the metal will not be converted to liquid state. And pure metal melts, flows down from the furnace, leaving behind the impurities. Okay. So from the name also you can remember this process, liquefaction. That means you are converting the metal from solid state to liquid state. That is why the name is such. Third method, electrolysis. So electrolysis, this method we have seen in detail in electrochemistry chapter. Remember, there we have seen that electrolysis, it is basically using electrical energy, we do some chemical reaction. So it is conversion of electrical energy to chemical energy, also known as electrolytic refining. In this process, refining a metal, mainly this type of metals, are refined by electrolysis method. And remember, in this method, obviously as it is electrolysis, there will be some anode, some cathode. In the cathode, you will take the pure metal. So suppose you are purifying copper. So what you will take? You will take pure copper in as cathode, and you will take the impure copper that you are actually trying to purify. That should be taken in the left hand side, that is in the anode. Mostly by convention we consider left hand side, there is anode. Okay. So crude metal, that is the impure metal, it will be treated as anode, and in cathode we will take pure metal. So gradually what will happen? The crude metal which is in anode, that will be corroded, and there will be deposition of pure metal in the cathode. Okay. Electrolytic solution, you will take some salt of the same metal. So if you are trying to purify copper, you can take any salt of copper, like copper sulfate. Okay. So here we will describe the process with the picture. See, as anode we have taken impure copper, and gradually it is corroded. Why? Because here copper is converted to copper 2+. Okay, and electrolyte we have taken CuSO4. So here you will have both the ions sulfate ion as well as Cu2+. The pure metal is obtained at the cathode. Why? Because at cathode it is already pure copper, that is the electrode, and here oxidation is taking place in the left hand side, and these electrons now it will be taken by copper 2+, and it will be converted to pure copper, and this pure copper will be deposited here. See, there is deposition of copper, and pure metal is obtained at the cathode when the electrical current of sufficient voltage is applied by dissolving impure metal at the anode. So anode, gradually the size of this electrode will decrease, and here size of the cathode, that will increase. Now see, here one particular term is mentioned which is very important, dissolving impure metal at the anode. Now this impurity, see, the impurities are deposited in the surface, lower surface of this container. Anode mud, it is called anode mud because it is generated from anode, and this contains all these metals. See, all these metals are actually very costly, and they are also inert in nature. They do not take part in reaction very easily. Silver, gold, platinum, all these are very costly metals. So from anode mud we can recover these impurities because these are very important metals. Okay, so this is known as anode mud or sludge. There are some other impurities which are, these are actually impurities because you are purifying copper. Suppose it is 80% pure, that means rest of the 20% there may be presence of silver, gold, PT, then Zn, Fe, etc. But Zn and Fe, they can be easily converted to 2+ form. Okay, but silver, gold, PT, as they are noble metals, they will not be easily converted to the oxidized state. So that is the reason, as they are in zero state, they cannot be in the solution. Copper sulfate electrolyte that you have taken, all these metals, they cannot remain in the form of cathode. So that is why they are already in metallic state. So they will not be dissolved in this solution and they will be deposited here. But the other impurities like zinc, iron, they will be in the form of cation. So that is why they are in the solution medium. Okay, but not silver, gold and Pt. This method that we are discussing now, this is actually electrolytic refining or electrolysis. But remember, we in today's class we also have discussed electrolytic reduction. But this is under isolation method. That is the second step. But electrolytic refining, though the terms are very, it sounds almost similar, but they are not same. Electrolytic reduction method, it is under isolation step. But electrolytic refining method, it is under purification step. So they are not same. When it is electrolytic reduction, our purpose is to reduce the metal. But when it is electrolytic refining, the purpose is to purify the metal. Okay. Metals are obtained by electrolysis of their molten salt. So suppose if you are using Na plus salt, it will be converted to Na. So from +1 state, now it is 0 state. But this is impure metals are defined electrolytically. That means the metal is already in 0 state, but you are further purifying it. So obviously these two methods are not same. One is reduction method, another one is purification method. This is extraction process of metal, that is isolation. This is purification process. In this case, metals are deposited at the cathode. In refining method, impure metal is made of anode. That is the metal that you are actually trying to purify. You have to take it in the anode side. And a strip of pure metal, that is a metal that you are trying to purify, you have to take that metal in pure form. A strip is fine. So in the cathode, a strip of pure metal we have to take. It precedes electrolytic refining. Precedes means first this method you have to do because it is isolation. It is second step basically. This is third step. So obviously it precedes electrolytic refining and it succeeds electrolytic reduction. Only after reduction you can do the purification process, not before that. So these are the differences between electrolytic reduction and electrolytic refining. Is there any doubt? Number 4th method, zone refining. So see, we are using the term zone. That means zone specific refining. It is based on the principle that impurities are more soluble in the melt than in the solid state of the metal. So suppose you have any impure metal in solid form. You are heating it and now it is in melted condition. Now when it is in melted condition, now you have both pure metal as well as impurities. But in this melted condition, impurities are more soluble, but metals are less soluble. This is the principle. So what we do in this process? In this process, impure metal is attached to a circular mobile heater at one end. Look at this picture. We have taken circular mobile heater. Mobile heater means the heater can move. So this is the mobile heater we have taken. This is the source of heat and this is the rod of impure metal. So now we have taken this circular heater in the left hand side. We have started from left hand side. Okay, and here we have taken germanium metal. Okay, so germanium metal, that is Ge. We have taken impure germanium metal and we are trying to purify it. So first, when it is in contact with this circular heater, there will be molten zone. So this is the molten zone. Only this part is molten, rest of the part is solid. Molten zone containing impurities. But as we have said that impurities are more mobile, more soluble. So what will happen when it is in molten state? Impurities gradually will be shifted towards right hand side. So, and the pure metal that will be that is, it will be present in crystallized condition in the left hand side. So gradually left hand side of the rod will be pure form of metal, right hand side of the rod will be containing the impurities. So in this way you that is, now it is having position here, next it will be having another position, then another position. In this way ultimately it will reach the right hand side extreme and all the impurities will be deposited here. So up to this part it is pure germanium, this part is impure. So what we will do, we can cut this portion. So as the heater is moved, pure metal crystallizes out, impurities will be passing on to the adjacent part of the metal because impurities are more soluble. This is the principle based on which we are doing this process. Okay, in this way the impurities will be accumulated at the other end. In this case it is the right hand side end where the impurities will be accumulated, I for impurity, and ultimately other end of the rod which is cut in order to obtain pure metal. So this part if you cut it, you can get the pure metal. Okay, now zone refining, remember it is used for germanium, silicon, gallium. So these two are group 14 element, gallium is group 13 element, indium is also 13, boron is also 13. So basically for group 13 and 14 elements this method is used. So metals such as this are made free, though boron is not actually metal, but boron can also be purified. So that is what is mentioned here. But if we focus on metals, it is mainly these examples. Okay. So zone refining, if it is asked that it is used for which metals, answer will be group 14 and 13 metals. Okay. Number 5th method, cupellation. This method is used for noble metals like gold, silver. It is noble metal because they are inert in nature. They are very stable in their zero state, that is metallic state. And these two metals are purified from base metals like Pb, lead, copper, zinc, arsenic, antimony, this one. So when the impurities are this kind, that is some other metals, unwanted, and you want to purify gold and silver from this type of impurities, then you can use this method. So in this method, what is done? Impure metal is taken in a cupel. Now what is cupel? Cupel is flat porous dish which is made of a refractory high temperature resistant material. Okay. Now why high temperature resistant material? Because we will there will be blast of hot air. Hot air means temperature is very high, so that is why it must resist this high temperature. So impure metal is taken in this cupel, so that is why this method is known as cupellation, and it will be heated by blast of hot air. Impurities will be oxidized. So all these impurities, they will be oxidized, and these will not be oxidized because they are very stable in their metallic form, and partly vaporized also. Both are possible, and partly absorbed into the pores of cupel. So by 3 methods basically impurities are removed. It may be oxidized. So suppose if it is copper, it will be converted to Cu2 plus. It may be vaporized. That means from metallic state, it can be converted to vapor state, or it can be absorbed into the pores of cupel. So in this way, impurities can be removed. Number 6 method, polling. Polling is a method which is used to purify metals that have oxidized impurities. So see, as we have mentioned when we have started different processes of purification, we have mentioned then that different processes are basically based on what is the nature of impurities as well as nature of metals. So you can see when your impurities are already oxidized in nature, then only you can use this method. So different methods, different principles, different conditions, both for impurities as well as the metals that you are trying to purify. It is typically used to purify metals like copper and tin that are in the impure form of their oxide. So suppose you want to purify tin. It is 70% pure. Rest of the 30%, there is some amount of its oxide present that you want to remove. because that is not the desired part. So we can use this, now we can use this polling method. In this method, a log of wood that is still green, basically green bamboo is used. Now what is the reason that specifically we have to take green bamboo? There is some reason behind that. So we have taken the molten metal containing impurities and we are stirring it with this green bamboo. And green bamboo, basically it contains some hydrocarbons which has reducing property. So these hydrocarbons will act as reducing agent and they can reduce this metal oxide. That is, if you consider tin oxide, it can reduce metal oxide to corresponding metal, and the oxygen will be removed in the form of CO2 because it is hydrocarbon. That means carbon is also present. So carbon will take this oxygen and it will form CO2, and it is gaseous, it will be easily removed. Okay, so in this method we use green bamboo, which is the source of reducing agent. It will reduce these oxidized impurities. So that is why it is important, when the impurities are oxidized metal form of the metal that you are trying to purify, then only this method is possible. Any doubt in cupellation and polling? Number 7, vapor phase refining. Vapor phase, that means there must be, that is, we will convert the impure metal to vapor form. That is why we are calling the name as vapor phase refining. Okay. In this method, the metal is converted into its volatile compound, because if the metal is not converted to volatile compound, we cannot convert it to vapor phase. So that is why first the metal that you are trying to purify, you have to convert it to volatile and then collect it elsewhere. Now this volatile compound will be decomposed further, that is the second step, to give the pure metal. Now this is the method, but here two requirements you have to maintain. So what are the requirements that must be present? The metal should form a volatile compound with an available reagent, because if it is not forming any volatile compound, vapor phase refining is not possible. Second requirement, volatile compound should be easily decomposable, because in the second step, basically this volatile compound is decomposed. So if it is not easily decomposable, then our purpose will not be fulfilled. So only when it is easily decomposable, recovery will be easy. So these are the two requirements. Okay. Now under this vapor phase refining, for nickel metal there is a specific method, that is, there is a specific term for this Mond process. Remember, this is only for nickel. So in this process, what we are doing, suppose you have impure nickel, so it is containing some impurities also with it. You are treating it with carbon monoxide at this temperature. So now what will happen? Only nickel will form this type of carbonyl complex, but impurity will be left behind. Now it is volatile, so it will be in the form of vapor, leaving behind the impurities, because impurities are not converted to vapor. Only the metal which is we are trying to purify, that will form the carbonyl complex. Now it is volatile in nature. So that is why in the second step, when we are decomposing it, again we are getting the pure nickel. Okay, and CO is the byproduct. So here carbonyl is subjected to high temperature. In the second step, see, this temperature is higher than this one. Okay, so that it is decomposed, giving the pure metal. So Mond process under vapor phase refining, that is for nickel. And there is another method which is known as Van Arkel method. This is for Zr and titanium, zirconium, titanium. Both are transition metals. Nickel is also transition metal. This method is very useful for removing all the oxygen and nitrogen impurity in zirconium and titanium. So what we do, crude metal is heated in an evacuated vessel with iodine. That means now the metal will form iodide. This metal iodide is more covalent. it will volatilize. That means, as we have said, that the requirement is the compound must be volatile. It should form volatile, otherwise our purpose will not be fulfilled. This metal iodide next decomposed on a tungsten filament, which is basically the source of heat, and pure metal will be deposited on the filament. So here we have the corresponding equations. Zr in impure condition, treated with iodine at very high temperature, it is forming this volatile compound. In the second step, which is decomposition, now further temperature is increased. It is done on tungsten filament, and we are getting pure zirconium iodine is reproduced. And for titanium also, now at 523 Kelvin, first we are getting TiI4, just like Zri4, and further in the second step temperature is increased and it will be decomposed to pure titanium iodine is regenerated. Okay, so Van Arkel method, it is for Zr and Ti. So in vapor phase refining, basically we purify nickel, zirconium, titanium. Fine. Related to this method, we have a question here. Which method of purification is represented by the following equation? This equation we have just seen. Sometimes the temperature that is mentioned, it may not be exact. It may be plus minus something, but that is not important, because if it is close to that temperature, it is same. But here, first we are making volatile complex, and in the second step we are decomposing it. So obviously it is vapor phase refining. But if you look at the options, cupellation. In cupellation, what we use cupel, but here we are not using that. In polling, what we use green bamboo. That is also we are not using. Zone refining. In zone refining, we use some circular heater like this. But here also we are not doing that. So this is vapor phase refining, but direct the name of vapor phase refining, that name is not given. But Van Arkel method, which is basically for Zr and titanium, that is mentioned. So option C will be the correct option. Next question. We have to find correct statement. The first statement, zone refining process is used for refining of titanium. Now this is obviously not true, because see, just in the previous question you have seen titanium is purified by which method? Van Arkel, and which is basically vapor phase refining method. So it is not done by zone refining. Zone refine, remember, we have done it for group 13 and 14 elements, not titanium. Then zincite, it is a carbonate ore. Okay. Now zincite, it is not carbonated ore. It is basically zinc oxide. So this statement is also false. Froth stabilizer is aniline. Now this is correct. Though Froth stabilizer, it is we have discussed it in the first step of metallurgy, which is basically concentration of ore. Okay, so there we have seen how Froth stabilizer is used, which is basically organic type of compound, aniline. This is correct. And the last statement, it must be false, because only one statement is correct. Sodium cyanide, NaCl, cannot be used in the metallurgy of silver, but we have already seen that NaCl we use for to make silver cyanide complex, and then this silver cyanide complex, remember this type of complex we have seen. This is further treated with zinc, and this Ag is now reduced to 0, and this place is taken by Z. So basically we use NaCl for metallurgy of silver. So this statement cannot be correct. This is also false. So here correct statement is option 3. So today we have discussed up to vapor phase refining, but one more method, which is chromatographic separation, which is the 8th method. It's the last method we will discuss under purification. That will be done in the next class. So considering all the slides, is there any doubt? So we will end the session here. Thank you for listening.